right, so lesson 42 is on vector operations and component forms. So today we're going to talk about like adding and subtracting vectors, and then eventually we're going to talk about like what it means to multiply vectors, and there's two different ways to find the product of vectors. Okay. So number one, so it says suppose u is equal to 5, negative 2, and v is negative 3, 4. So I want you to sketch both of those vectors on the same. Julian, over here. You see here? You guys give him the packet. All right, so if I'm finding u plus v, let's see what it looks like geometrically first. So if I have 5, negative 2, it points towards this point right here, right? So our vector goes in this direction. So that's going to be u. And then v is negative 3, 4, so it's going to point towards the point negative 3, 4. Like that. So that's vector v. So a couple of you guys were absent last time, so we would find the magnitude, the length, which often has like an absolute value around it or the double absolute value kind of sign. And we would find the direction, meaning we'd find this angle here. That's really no different than what you guys have done in the trig sections, right? All right, so in this case, we want to add these two vectors together. So if I have the vectors 5, negative 2, and I want to add it to negative 3, 4, does anybody want to make a guess at what the result is? Because you're probably right. What do you think the result is going to be? Yep, exactly. It's going to be 2, 2. Okay, so let's look at where 2, 2 is. So 2, 2 would be a vector that goes right here. Okay, that's 2, 2. So what we do when we add two vectors is we take the first vector, or really the second, doesn't matter because we're adding, right? But let's say I take vector u, and I start with that. And then vector v, I have to go back 3 and up 4, right? So from there, I'm going to go back 3, so 1, 2, 3, up 1, 2, 3, 4, right there. And I draw on that line. Do you guys see how I just moved vector v to another location? So this v that we had before, it has the same magnitude and direction as this red line that I drew.
Why?
Okay, so we're moving it to the end of u. So when I do u plus v, I didn't draw it very well. It should match up with that blue line. I should have done a grid on this so it's nicer, huh? So I have 2, 2. My 2, 2 got a little crazy. All right, so it's like somewhere around there.
So it's supposed to match up?
It is supposed to match up, yeah. So what ends up happening is you connect the origin, right, your 0, to that ending point where it connected. Okay. So if I have, on the next one, well, if I had, let me do another example. So let's say I had a is negative 2, 1, and I had b was 3, 3. So I would do my negative 2, 1, so that would be going in this direction. And I'd add my 3, 3, which goes in this direction. So what I do is I start with my first vector, and then I add the second vector to it in that same direction. And if you do it correctly, you should get the two things added together. So negative 2 plus 3 ends up being 1. 1 plus 3 ends up being 4. Does that look like it's the vector 1, 4? Yeah. So our resultant vector is what we call it, is right there.
Sorry, how do you move the, like for A, how do you move vector V down to U?
You can just move it wherever you want, but we're going to move it to, in order to add vectors, we move it to the tip of the last one. So wherever, so see how that's the tail to the tip?
Yeah.
So we add it to the end of the last one. Okay. All right, so we'll do some more of these. I know it's kind of weird. All right, so if I have 2u, any guesses at what 2u is going to be? Yeah, you're just going to multiply by 2. We're going to get 10, negative 4, because we would have the 5, negative 2 added to another 5, negative 2. So let's look at what this is geometrically. So we're going to have u, which was 5, negative 2. I'm going to put grids in next year. That would really help on this problem, wouldn't it? Gotta love grids. All right, so I'm going to have 5, negative 2. And then I have 10, negative 4 is what I'm trying to get. So see what I'm doing is this is one of the u's. And I'm going to add it to itself. So what happens is it goes in that same magnitude and direction as before. So we end up getting 6, 7, 8, 9, 10, 10, negative 4. So it goes right towards that point. Does that make sense? Do you guys see what I'm saying? So that's 2u. All right, so what do you think would happen if we had like half u? Yeah, it gets smaller, right? So we'd have 2.5 comma negative 1. It would have a smaller magnitude. But what about the direction, the angle? The angle's the same, right? Does that make sense? So we're talking about the magnitudes when we're doing this. So if I have 2u plus 3v, so go ahead and write what you think it is. So we had u was the vector, I don't remember what vector, 5, negative 2. And then v was the vector negative 3, comma 4. So if we have 2u plus 3v, and when we draw this on paper, a lot of times we'll put the little harpoon over it. Because we can't bold. Like, how do you make something bold, right? So it looks like we're going to have 2 times 5, so 10, added to 3v, so added to negative 9. And then I'm going to have 2 times u, which was 2 times negative 2, so negative 4, added to 3 times 4, which is 12. So it looks like we should get 1, comma 8, right? Did you guys see that? Okay, so geometrically, what are we doing? So we had the 2u, which we had just done, so we had 5, comma negative 1 for u, right? So it's like we're taking it here, and then we double it.
Well, when we have like 2u, do we have to count in instead of 5?
Like count over 5 and down 1. Yeah, technically, like if you had a grid 1, 2, 3, 4, 5, you would go again. Yeah. Oh, is it 5? Did I mess that up? I think oh, so I did negative 1. I wondered why that looked different than the last one. Okay, so 5. I'm just going to be fancy here and just adjust my, I didn't quite make it, but you know what I'm saying. Thank you. All right, so we have 5, comma negative 2, so then that's going to be 10, comma negative 4 for the 2u, right? And then our v was negative 3, comma 4 right here. And so what's going to happen if we have 3v? Right, that's going to triple in size. So it's going to go another one and another one. So what Kate's saying is, should we do like the little markings? Yeah, you can, but if you're just trying to like estimate and see what the sketch looks like, you don't have to be like super, super precise. But if you're trying to actually find this point from a sketch, you probably want to draw on those lines, right? So what this sketch does is this part that is right here, I'm going to move it, and I'm going to move it to the end of the red line, okay? So it's going to move over here. Okay. And then we would get our resultant, which is this one, of 1, comma 8 if we move it. Does that look like around 1, comma 8 on your paper? Yeah. Does that make sense? So our resultant, we always kind of move one of them and then we connect from that origin. Okay, so vector addition and scalar multiplication. So it's really not terribly difficult. Addition, we just add the components, add the x components, add the y components. Multiplication, we just scale both components, meaning we multiply by like 3 or 2 or whatever. So if we have u plus v, it ends up being u1 plus v1, comma u2 plus v2. And then the product of k times u is going to be k times u1, comma u2, which ends up being k u1 and then k u2. You guys understand all those symbols? Just multiplying things in. So for example, like we said, if we had 1, comma negative 3 and we added it to 2, comma 5, our resultant should be 3, comma 2. Nothing that is like blowing your mind, right? It's like, oh, I'm going to add my x's and add my y's. That's pretty easy. And if you had, 7 times 2, comma negative 5, that resultant ends up being 14, comma negative 35. So it has the same direction, but now that magnitude is going to be 7 times bigger. Okay? Not yet. Speedy. All right, so there's 2 ways geometrically that you can draw this. So the way that I do is kind of with that little triangle, which is part of a parallelogram. Okay, so it says there's two different representations of this vector addition. So one is the tip to tail. So you start with the tip of the last one and you connect it to the tail of the next one, right? So in this representation, we move the second vector to the end of the first vector and draw a line. So that's what I was doing. I was saying we had our first vector, and then let's say our other vector went in this direction. Well, we just took that and we moved it, and we put it on the end, right? When we do that, our resultant is right here. Okay, what this does is, since our original one was right there, is we've kind of created a parallelogram if we connect that blue line. Do you guys see? So we have half of a parallelogram. We have that like little triangle drawn in. So some people like to draw in that full parallelogram. So that's fine. So in this case, if I have A and B, what some people will do is, instead of moving it, which is hard for me, I always have to think about it moving, is they will just draw the resultant. Well, they'll draw that kind of that parallelogram in, and they'll say, oh, the resultant's going to be right here. Okay, does that make sense? How it's the same thing? Because basically you're taking this and you're moving it here, and then they're drawing that resultant. Okay, you can do it either way. All right, so next one. So if I have u is 4, negative 3, so let's kind of practice this sketching. So 4, negative 3, just like that. And we have v is negative 1, negative 5 is here. Oops, got a little crazy on that one. Still doesn't quite look like 1, 2, 3, 4, 5. More like that. So I have my u and my v. So if I want to do u minus v, so what do you think I'm going to do if I have a minus v? What would happen to it? So if I have negative v, I previously had v was negative 1, negative 5. What do you guys think negative v is going to be? 1, 5. What does that do to this vector? So instead of being in the third quadrant, which quadrant does it go to? The first, because it ends up being like a reflection. So 1, 2, 3, 4, 5. So it goes like right over there. Do you guys see what I'm saying? So this is negative v. You're so confused. Did I lose you?
So what do we do?
Well, we haven't done anything yet with the u. So we're trying to do u minus v. So in other words, u plus a negative v. So we took care of that negative v, right? So now I want to add these two together. So I want to add the blue one and the u together. So what do you think we're going to do geometrically? So that's where we're going to think about that parallelogram, right? So I'm going to take this v and I'm going to move it right here. So our resultant should be, if we've done it correctly, right there. Okay, that ends up being u minus v. Okay, so what do we think the numbers are? So if I have u minus v, I had 4, negative 3, and I'm subtracting out negative 1, negative 5, right? Or adding the negative. So if I add the negative, it's adding positive 1, positive 5. So I should get 5, 2. Does that look like 5, 2? Yeah, it looks pretty good. Mine's a little bit off, but yeah, it should look like that. Does that make sense? And you can count the vector, and you can be like, oh, I'm adding v, which is, you know, if I counted from here, that point was 4, negative 3. And if I say, oh, I'm going to add vector negative v, I'm going to add positive 1 to the x, right? And I'm going to add 5 to the y. Does that put us where we want? If I add 1 to the x and 5 to the y? Yeah. Okay. You guys are looking so confused. I don't feel like it's that hard. Is it hard? All right, so what's negative u going to be? We don't have to draw a picture, but what's negative u? Negative 4, negative 3. Can you guys visualize in your head on this picture?
Would it be positive?
Oh, did you mess me up?
No, I said
Oh,
positive.
I just wrote the wrong thing. All right. Negative 4, 3. So think about on this picture where it's going to be. Negative 4, positive 3. Does that go in the opposite direction of u? That's what happens. So it flips it around. It goes in the opposite direction. Okay? All right. So evaluate the following. So we don't have to draw the pictures now. So what if we have u plus v? What do we think it is? Well, we look at our u and we look at our v. So we end up getting negative 1, negative 1, like that, right? Because we had negative 2 plus 1, and we had 3 plus a negative 4. Easy? U minus u. 0, 0. That's called the 0 vector. You write that like that. Do you know what the 0 vector is? It has no magnitude, no length. It's like nothing. That's what 0 is, right? Nothing. So it's like at the origin and there's nothing there. All right, 0 plus 3z then. Well, it's just going to be equal to 3z. Yeah, exactly. So negative 21, comma, negative 15. Notice how I'm writing the z with a little harpoon over it because it's a vector. All right, so 5 plus 2w. Well, don't you think that's just going to be 10w? Yeah, because you would find 2w, so you'd multiply 2n, you get negative 2 comma negative 6, and then you multiply the 5n. So can't we just do that all at once? So yeah, this is going to be, what did you guys say? Negative 10 comma negative 30, got it. All right, and then 3 plus 4 comma, or 3 plus 4 multiplied by the vector u. Yeah, it's the same as 7u. I mean, these are all things that you've learned before, right? It's really the same as all the properties we already know. So 7u is going to be negative 14 comma 21. Perfect. Easy. All right, so it says previously we found the angle of a vector by using the formula tangent of theta equals y over x. So if you guys remember last time, if we had a vector, so you don't have to draw this, just going to look up here. If I had a vector and it was 5 comma 3. If I wanted to find the angle, the standard angle, just like our unit circle, if I wanted to find that angle, what we do is we draw a little triangle in. And we're like, oh, this is 5, this is 3, I want to find theta, right? And so we do that by saying tangent of theta is equal to opposite over adjacent. And we solve for theta. Okay? And if we used our calculators would give us the right answer for the first quadrant. But you know how inverse tangent is between negative pi over 2, so negative 90 degrees and 90 degrees? If I did something in the second or third quadrant, it's not going to give me the right answer. And even in the fourth quadrant, it's going to give me a negative answer where I need to add 360 to it, right? So sometimes we have to adjust those thetas. Okay. So we're going to go in the opposite direction. We're going to say, well, what if we don't have, you know, our vector? What if instead we have the angle and the length of the vector, and we want to find the x and y components? All right, we do exactly the same thing, just in reverse, okay? You didn't have to. You guys are all erasing. You guys can keep this on your notes. It's fine. So what if I have the angle is 25, and our length of the vector is 10? Okay, that's our magnitude, right? Can you find the x and y that go with it? Yeah, so what we do is we draw this little picture. And we do SOHCAHTOA. I heard someone say SOHCAHTOA. Right? This is going to be our x distance. This is going to be our y distance. We could do tangent, but look, if I want to find x, should I do tangent? Yeah, so let's do sine. So we have our SOHCAHTOA. I love how some of you guys still write it on your paper. So I'll write it for you. You're like, I can't remember the order without writing it. So we have opposite. Well, let's find the x first. So I have adjacent and hypotenuse. So let's do cosine. So I'm going to say cosine of 25 equals adjacent over hypotenuse. In other words, my x ends up being 10 multiplied by cosine of 25. Okay, and we can find that. Okay, so that's a decimal. I would round to 3 decimals, like I always make you. Make sure that you're in degree mode. So we're going to have 10 cosine of 25. So I got x is equal to 9.063. And that makes sense. It was a really tiny angle, right? 25 degrees. So I know that this side isn't going to be as long as 10, but it's going to be pretty long because that's a small angle. Okay. How about y? Well, for y, I have opposite and I want hypotenuse. So I'm going to have sine of 25 equals y over 10. In other words, y ends up being 10 times sine of 25. So if I find that one, it ends up being 4.226. Okay, that's my component form. Ben, you with me? I love when I get you guys first period. You just look so enthusiastic, ready for the day. Have you been struggling since the time change? I've been struggling since the time change. I'm just up late. All right, so component form, whenever you see that just means find the x component, find the y component. Easy enough? Do you guys think that it will always be like the hypotenuse times the cosine of the angle for x? I don't know. I think it will be. Because it's always going to be x equals the adjacent over the hypotenuse. Adjacent is always x, right? Or sorry, not x equals, cosine of the angle equals adjacent over hypotenuse. Okay, so that's how we resolve the components of a vector. So when it says resolve the components, it means find the x and y values for the vector. Okay, when you see this, because I'll write this on test questions. Resolve the components. You should know what that means. That's the blinds in the other room. All right, so we end up getting our magnitude of the vector multiplied by our cosine of the angle. Okay, so I'm going to write it like magnitude of v, and you can put the double lines if you want, cosine of theta, comma, magnitude of v, sine of theta. Okay, but remember, you can always draw the picture. Okay, so when I teach math, I don't have people just memorize tons and tons of formulas. Okay, that was never my skill when I was in school. I would forget formulas or leave off a negative or something like that. Or switch the cosine and sine, right? Although you shouldn't switch cosine and sine because cosine is the x value, right? Think about the unit circle. Sine is the y value. That's why it's in that order. But I was very good as a visual student. That's why I was an art and math major in college. I liked drawing things. So if you can sketch the picture and you can say, oh yeah, this is just SOHCAHTOA, I remember how to find x and y, then you're good, right? So you don't have to memorize every single formula in pre-calc. Okay, you should know where they come from. So this one, so it says find the component form of the vectors with the given characteristics. So what this is saying is we're along an angle of pi over 6, so we're in radians now, and our length is 3. So we're asking, can you find the x and the y? Yeah, it's the same thing, right? So if I'm finding it, I'm going to do 3 cosine of pi over 6, which is 30 degrees, as Kate's saying, right? And then 3 sine of pi over 6. So I'm going to have 3 times, do you guys know cosine of pi over 6? Root 3 over 2. And 3 sine of pi over 6 is 1/2. All those unit circle things coming back, aren't they? They never leave. I told you when we first learned them, they would never go away. You didn't believe me. All right, so we get that. We have one more chapter with trig stuff after this one. And then we're going to do other things. All right, so next up. So what if I have theta is equal to 300? Well, that's going all the way around, right, to like right here. Okay, so in order to do this, we use what we call a reference angle. So I would put 60 degrees right there. And I'd say, oh, this is 100, right? And you could find your x and y components, so x and y, using SOHCAHTOA. The only thing that would be weird here is if you're using that 60 degrees, you're going to get things in the first quadrant, right? So you're going to get sine and cosine. You're going to have your x and y values are positive and positive. What should x and y be? Should they be positive, positive? Positive and negative, right? So we're in that fourth quadrant. Okay, but if you put it into the formula just as is, if I just do 100 cosine of 300 and 100 sine of 300, it will actually give me the signs that I want. Okay, so you don't have to draw this picture out every single time. You can go straight to our magnitude times cosine of theta and our magnitude times sine of theta. Okay, so if you think about 300 degrees, right, which is where I just drew it in the first place, cosine is going to be 1/2. Sine is going to be negative root 3 over 2. So we end up getting 50, comma, negative 50 root 3. That's our component form. Easy so far? Are you worried it's going to get harder?
Is it gonna be on?
It's not that bad. I mean, we're going to go back to bearing. You guys remember bearing? You guys didn't like bearing, but we've kind of previewed it, so the second time you see it, you'll be like, oh, bearing. That's how math is. It's like the first time you see it, you're kind of like, meh, I don't know about this. And then the second time, you're like, oh, this is easy. All right, so find the direction and magnitude of the following vectors. All right, so we have it in kind of in component form, but we don't know what that x and y values are, right? But it's set up so we can kind of find it. So if I have 2 cosine of 60, so think about your 60 degrees right here. So I'm going to have 2 times 1/2, and then 2 times root 3 over 2. So I get 1 comma root 3. That's a 2. All right, that's the component form, the x and the y, right? And so I'm asking for the magnitude. What does that mean? Length. So I want to find the length. So I do that by, I'll call it v. Doing the square root of the x value squared plus the y value squared. So 1 squared plus root 3 squared. Again, right, if you have 1 comma root 3, what are we doing? We're just finding that length, d, using the Pythagorean theorem. Okay, so that's not anything that's new to us, right? We're just finding the hypotenuse, basically. So we end up getting 1 plus 3, which is 4, so the square root of 4 is 2. So that's the magnitude. What's the direction? 60 degrees. Tell me how I could do that without doing any of that math that I just did. Yeah, exactly. Look, guys. Magnitude, direction, right? It's all set up for us. Do you guys see it? I know, tricky, tricky. All right, so remember these ones with the zeros? So -5, comma 0, so we're going in this direction. Can I get the magnitude and direction without doing any work? Yeah, what's our magnitude? Yeah, it's 5. Magnitude's always a positive distance, right? And then our direction, what would be our theta? 180, right? We're going around that direction, so we're saying 180 degrees. Or pi if you wanted it in pi, like in radians. Easy enough? So if I give you one, are you guys going to be tricked? So if I say 3 cosine of pi over 4, 3 sine of pi over 4, what's the magnitude? What's the direction? Magnitude is 3, direction is 45 degrees or pi over 4. Right? Perfect. All right, so the next one. So this is the last little bit. So sometimes it's really useful for us to have things that are of a length 1. And the reason we do that is because then if it's a length 1, we can easily scale it to whatever we need it to be. Okay, like imagine, I don't know, like think about like my geometry class just did scale models of their bedroom, right? It was easy for them to be like, oh, 1 inch is equal to 1 foot. And then they can change everything and they can be like, oh, if I want it to be 17 by 23 feet, it's going to be on my paper 17 inches by 23 inches, right? Okay, so it's nice to scale things down to a unit of 1 so then you can multiply it and adjust it however you need it to be. So it says a vector with magnitude of length 1 is called a unit vector. Also think about our unit circle, right? Length of 1. If v is not the 0 vector, then the vector u, so which is a unit vector, ends up being our vector v divided by its magnitude. Okay, this will make more sense when I do one. So find a unit vector in the direction of 5, -2. So if I have 5, -2, 1, 2, 3, 4, 5, right there. What is the magnitude of v right now? So what's the length of v right now? Sorry, I always do one line. Square root of what? So we're going to have our 5 squared plus -2 squared, right? The length. So we get the square root of 29. Is that a length of 1? What's square root of 29 between? What two whole numbers is it between? It's bigger than square root of 29. You guys can't estimate this in your head. It's bigger than 4. Yes, thank you, Nick. So it's bigger than 5 and it's smaller than 6, right? It's between 25 and 36, 29. So right now it's like, I don't know, 5.5. Not really, but somewhere around there. We want to scale it down so it's only a length of 1. Okay, so if I want to make it smaller, so it's only a length of 1, I'm going to multiply it by some number, or divide it by some number, right? So what I'm going to do is I'm going to take this vector v that I had before, and I want to make it a length of 1, so what am I going to divide by? I'm I'm going to divide this out. I'm going to divide by square root of 29. That's going to be my vector u, which is a unit vector. 1 unit in length. So the way we write this is 5 over root 29, comma, negative 2 over root 29, like that. Some of you guys are going to be crazy and try to rationalize that. I don't care. If you want to rationalize, go for it. It seems like extra work to me, right? All right, so now we're going to verify that it's a length of 1. So I'm verifying that it has a magnitude of 1. So I'm going to take this vector that I just found right here, and I'm going to find its magnitude. I know that you guys don't like that and you're scared with it, but it's fine. Hey, girls. So I'm going to square it. And then I'm going to do negative 2 over root 29. And I'm going to square it. Yes, they're confused on the seating arrangement.
Yeah.
So we have 25 over 29 plus 4 over 29 equals the square root of 29 over 29, which is 1, right? So it does have a length of 1. Okay, geometrically, what has this done to this? It's made it just a tiny little vector that has a length of 1. So it's like right here. Ooh, really tiny. Side note, you guys all know this. So if I go over 1 and down 1, this is not a length of 1. Like, I have people that count squares all the time. They're like, oh, I have a grid on my paper, right? And so I have 2, 2, you know, they have like all these little grid boxes. And I have people that were like, oh, with vectors, this is going to be length of 1, length of 2, right? They're like, that's a length of 2. Do you guys know that that's not a length of 2? Do you know what length that would be? I don't know. This is 1, right? What's the hypotenuse then if I have 1 and 1? Root 2. This is root 2, right? Think about your 45, 45, 90 triangles. 1, 1, root 2. So I have root 2 and another root 2. That would be 2 root 2, right? So don't count like this way. Be like, oh, I'm just going to go out. 25. Yeah, that would be weird. Okay, do you guys understand the unit vector stuff? We'll try one more after your break. Uh-huh. All right, so unit vector in the direction of negative 5, comma, negative 7. So if I have negative 5, comma, negative 7, its current magnitude is not 1. Do we agree? So what's the magnitude of b right now? So it's going to be the square root of 25 plus 49. 74 maybe? Is it 74? I think 74. All right, that would be nice if it was 64 and it just worked out to be the nice 8, but it's 74. All right, so we have our unit vector then, we want it to have a magnitude of 1. So our unit vector has to be our negative 5, comma, negative 7, and we have to divide out by the length that it is. So if it was 10 units in length and we divide by 10, isn't that putting it at 1 unit in length? That's what we're doing. Okay, so we're taking this and we're dividing by root 74. So our unit vector looks like negative 5 over root 74, comma, negative 7 over root 74. Oops. And that's our answer. Easy? So now what if I wanted to take that vector and I wanted to make it a length of 2? I'd multiply that unit vector by 2. Does that make sense? So you can make vectors as big as you want by going down to the unit vector and then scaling in whatever direction you need. Yep.
So we only have to like do this squaring or yeah, we only have to multiply it, like squaring it if it says verify for 1.
Yeah, it didn't say like verify that this is a length of 1. We're going to assume it's a length of 1 because we did the directions like we were supposed to, right? We divided out by that magnitude. So we're good. All right, and then the last thing we're going to talk about is I told you that vectors we can write different ways. So we can do like a bold V, right? How do you do a bold V with a marker? So we can do a bold V or we can do a V with a harpoon. Or sometimes, you know, I say that sometimes we write like a little arrow over there. These all mean like vector V. Okay. Well, there's another way that we can write the component form. So when you see something like negative 5, negative 3, we can write it like that. Or we can write it as negative 5i plus negative 3j. So with i's and j's. All right, so I know that's a little confusing. This is more in the engineering world. They'll use i's and j's and so on. So it says unit vectors lead to the ijk representation of a vector. So vector I, so we have this like little hat over it. I don't usually put the little hat over it. Is 1, 0, and j hat is going to be 0, 1. Okay, what these mean are the unit vectors in this direction and this direction. So this is I hat and j hat. Okay, those I hat and j hat you can adjust by scaling them by multiplying by 5 and 4 and whatever you want. This is really not a hard concept. You guys are all looking like, oh my god, like you look like you're going to vomit right now. It's really not that bad, I promise. So if you take a lot of physics and or applied math like engineering, you will often need the K one, which is used for 3 dimensions. You guys remember in Algebra 2 when I had you guys draw things in 3 dimensions? Yeah, so you could have a vector like going in this direction, right, which is going out this way over, I don't know, like, do you guys remember that? You guys didn't really like it. So we could have things in 3 dimensions. We're just going to do 2 in pre-calc. So if I have negative 2i plus 3j, and I ask you to write it in component form, all we do is negative 2, 3. Can you handle that? It's not hard. You can handle this. What this means geometrically is we go over 2 and up 3. So it means we made our I component in the negative direction 2 units long, and we made the j component 3 units long, and we got this in the end. Okay? This is not anything that's hard. So if you have w plus u, and you see w is 1/3 I plus 9j, what does that mean w really is? It means that it's 1/3, 9. And u is really 2/3, negative 9. So if I ask for w plus u, what do we get? 1, 0. That's it. All right, make sense? All right, I think that's it. Oh, we got a couple more. So if I have this, so if I have 2v minus 3u, 2v minus 3u is going to be 2 times the 1/2, comma 4, so I'm going to have 1, 8, right? And then plus, I'm going to go ahead and multiply that negative 3 in. So I'm going to have negative 2, negative 1. So when I add them together, I should get negative 1, 7. Okay? Yeah, I think I went ahead and distributed the negative already. So you could do plus and then, or you could do minus and then have 2, 1 there. So if I ask you to write the final thing in ij notation, what would you write this as? Negative I plus 7j, done. So it's really not like dramatically different. We got this. All right, so find the magnitude and direction of the vector 4i of minus 5j. So if you want to rewrite it, write it like that, right? And we're finding the magnitude and the direction. So this is kind of a review of what we did yesterday. I would consider what quadrant it's in. It's in the 4th quadrant. So our angle in the end, we should have something between 270 and something between 360, right? We typically go from 0 to 360. So if we're in this 4th quadrant, we should be between 270 and 360. Our calculator is going to give us a negative number. So our magnitude of v ends up being 4 squared plus negative 5 squared, which is 16 plus 25. So the lovely square root of 41. And then if you forget how to find that angle, remember, I told you don't memorize all these formulas if you don't want to. This is our theta, right? We have 4 and we have negative 5. So our formula for theta is our tangent formula. It's tangent of theta equals opposite, which is always the y value, over adjacent, which is always the x value. So I'm going to have inverse tangent of negative 5/4. And my calculator gives me negative 51.340. But we want between 0 degrees and 360 degrees. So right now when it's saying negative 51 degrees, I mean, that's okay. That gives us something in the 4th quadrant. We just don't want that name for it. We don't want to call it negative 51. So what do I do to adjust it? Add 360. Perfect. So when I add 360, I do get a number between 270 and 360. I get 308.660. Yeah, that's it. So our magnitude and direction are listed. Easy enough? All right, so let's stop there. let me give you guys your homework.